For section 6.4, let's talk about the transport equation, which is a very specific PDE here that it's very similar to the equation we just discussed. So the transport equation, it's an equation of the form partial of u with respect t. Notice in this case the x and y are not involved. The variables involved are x and t. Okay, so and actually, still, this equation resembles A, okay, the equation AU with respect x plus B with respect y, plus B, U with respect y equal to 0. However, this is now U of t plus B U of x in this case. And then in this case, we will replace y with x and x with t. And in this case, a equals to 1 and, b equals to 1 and a equals to c in this case. No, b equals to c, rather. B equals to c, a equals to 1. That's the only difference. It's just a very particular and very special case of the general equation we discussed in the previous section. Okay, so, and the solution, I'm not going to derive it. I'm just going to use the solution to this. Okay. Now, how does that work? So, what we're going to do here is all we do is identify the value of c equal to 2. So, our solution, which is a function in space, in the one-dimensional space and time, as opposed to the previous case, which was a solution we were working on in the two-dimensional space where no time was involved. Here, it's a one-dimensional space and time involved. That's a function of x minus 2t. All right? And that's it. That's the solution to the equation. Well, what about the particular solution? So, if in this case, u, okay, let me do it here, u of x, 0, equals to 1 over 1 plus, wait, not yet, not yet. Let's do f of x minus 2 times 0 first, right? That is actually equal to simply f of x, isn't it? But what is that equal to? Isn't that equal to 1 over 1 plus x squared? Do we need to do any shifting here, any division like we did before? Not in this case, right? Mhm. No. So what do we do now? Okay. In this case, this is f of x. Okay. Now we're going to replace every instance of x with f of x minus 2t. With x minus 2t. That is 1 over 1 plus x minus 2t quantity square. And that's a solution. Let me write it down here more formally as a u of xt equals to 1 over 1 plus x minus 2t quantity squared. Okay? Now, what is this anyway? Because in this case, notice the variation we did in the variables was to let t equals to 0. But what if t were equal to 1, equal to 2, equal to 3, etc., or negative values? So, well, that's actually what describes or what gives a better description of what transport equation is. Let me show you what we mean by a transport equation with the graph. Okay, so let's see. So let's consider the solution right here where a equals to 0. Let me actually, where is that? Right here, hopefully. Okay, so that's the solution we got, right? So for t equals to 0, what I'm going to do, I'm going to drag, and do you see what happens? We get different shiftings in the solution curve, right? Well, what happens here is this curve is transporting to one side or the other depending on that particular or on that initial condition. So notice in this case, the larger the value of a, the transport goes to the right. Otherwise, it goes to the left. Okay, and well, you can relate this to what we have in our original equation. the coefficient, the positive coefficient tells us we're going to have a transport towards the positive x-axis. All right. Now let's have a look at another example. I'm going to do a bunch of this actually, so you can see how they work. Solve the same transport equation, but see in this case, all you need to see here is, or is to determine c equals -3. So the solution, the general solution, that is some function of x, however, minus -3t, that's plus 3t, okay? And we're done with the general solution to the PDE. That's it. We want the particular solution. That is when oh, okay, wait, u of x0 equals to f of x plus 3 times 0. That is simply f of x, isn't it? But what is u of x equals u of x comma 0? Isn't that e to the negative x squared? All right. Do we need to divide again by another number like we did in the previous section? Not in this case. That's a good thing about transport equation. You don't have to do a lot of the work. So now let me shift every instance of x with x plus 3t. So f of x plus 3t equals to e to the negative x plus 3t squared. Actually, that is more formally u of xy. No, now u of xy is u of xt right here, okay? U of xt equals to e to the negative x plus 3t, quantity squared, okay? Now, have a look at the coefficient c. That's going to change the behavior in a different way, slightly differently, you know? So, let me show you the graph for this one. Okay, let me get rid of this graph. Let me get rid of this text right here. I don't need that text either here. Okay, so the new curve right here for 0, and that's the label right here. I need the label. Yeah, I think I need it here. Okay, for whatever reason not working. Oh, there we go. So this is what I'm going to do. I'm going to use this slider and I'm going to slide to the right. But what happens? The solution now goes to the left. The transport goes to the left. Why is that? If you compare this equation with the one we just solved in the previous example, the positive coefficient tells us a positive transport. The negative coefficient tells us or indicates a negative transport. All right? Let's do one more. Let's do one more. You can see these ones are very quickly solved, right? All you need to look at is what? The value of c, okay? The value of c, which is, in this case, what is it? C equals to 2. That is, the solution u of xt will be some function of x and minus 2t, right? Now be careful time with the initial condition, okay? For this condition, we want to evaluate u of x comma -1, not the usual x of 0, x0. That is, I'm going to substitute f of x minus 2 times -1. Be careful here. That'll be actually equal to f of x plus 2, okay? Which is what's u of x minus 1, the given function, x over 1 plus x squared. Okay, guys, in this case, I want to know what f of x is, not f of x plus 2. What do we do on both sides of this equation to every single x to get f of x instead? Subtract x, right? Subtract 2, right? So f of x equals, I already subtracted 2, subtract 2 here, that's x minus 2, and be careful with the denominator, that's 1 plus x minus 2 squared, but the x minus 2 gets squared, right? Ready for particular solution? Yes. Substitute, substitute, substitute for every instance of x. It's just a shifting in the end, right? It's just a shifting. So f of x minus 2t equals to x minus 2t minus 2 over 1 plus x minus 2t minus 2 quantity squared. Kind of a weird solution, isn't it? Let me call this also u of x t equals to x minus 2t minus 2 over 1 plus x minus 2t minus 2, everything squared. I'm going to show you the graph. Of course, what do you expect the behavior of the transportation to go? To the right this time. Let's verify that. Let's see if that's true. Okay. So that is this function. So let's see. Let me use the slider. So that's the curve. And okay, that's a of -1. That's the graph of the particular solution. Let's get the one for -1. Okay. So let me drag to the right. Oh yes, the transport goes to the right. Great. All right. And guys, those were a couple of examples, well, three examples of the transport equation. Okay, guys, there is a special case of a transport equation that's called the transport equation with decay. Okay, so essentially it looks like the same PDE we saw a couple minutes ago. However, there's an extra term, partial derivative. So partial of u with respect to t plus c, partial of u with respect x plus a linear term in u. All right, that is au, and that equals to 0. The solution is given by u of xy. Actually, it should have been u of xt right here. Little typo, xt, some function of x minus ct, but this time times an exponential factor, guys. Okay, actually, I'm going to derive the solution to this equation. Although, actually, you could do it using separation of variables. Well, that may take a while. In this case, I'm going to take the same approach, changing the coordinates, So, by letting u of xt to be another function v of new coordinates. However, in this case, remember how in the previous case, we let the y variable to be the constant one? This time is the t variable. T is constant. Otherwise, they would have told us, oh, t changes in accordance with some equation. But no, it's just the variable c, this new Greek letter, this weird Greek letter. So, okay, so chain rule. Using the chain rule, I want to differentiate u with respect x, but I mean with respect t, So that is, I need to differentiate v with respect z, and then z with respect t. What's the derivative of the z function with respect t? Isn't that negative c? Okay, so that is v with respect z, that little symbol, times negative c plus v with respect t. But what's partial of t with respect t? Isn't that 1? That leaves us with negative c v with respect z plus v sub t, and let that be equal to 0. Wait, no, not equal to 0. I don't know why I said it equal to 0. Okay. And then what about the second, for the other partial derivative term in the PDE? So we need to differentiate v with respect z, okay? So that is v with respect z, but what is the partial of z with respect x? So that is the derivative of this function here with respect x. Isn't that 1? And then the second term goes to 0, so that times 1 plus v with respect t. But what is, okay, careful here. What is the derivative of t with respect x? Hmm? What is the derivative of t with respect x? Keeping in mind that t is constant, differentiate t with respect any variable in the universe. That's times 0. Let me do a dot instead. So that is plus, or just v, right? Just v sub c. Okay, let's substitute into the PDE. So partial of u with respect t, which is negative c v with respect z plus c times the partial with respect x, which is v z plus a u. But what's u, guys? In this case, u equals v, isn't it? U equals to v. Everything is in terms of v. We will go back to the world of u again in a minute. Okay, boom, boom, cancel out, right? Cancel this out. Wait a minute. I believe I was missing a term right here. Hold on. Hold on. Right here, I'm missing this v sub t, right? Plus, okay, here we go. So that's going to leave us with v sub t equals to, plus a, AV. And well, did you see how this PDE right here is really an ODE? Because only one partial derivative appears, only one variable with respect to it's showing here. So what does that mean? V sub t. Actually, let me change this to dv dt equals to negative AV. And in this case, separating the variables, dv over v equals negative a dt. Integral, integral. Keep going. Ln of v equals negative a t plus some constant of integration. But guys, since really there are two variables involved in this problem, we're integrating with respect t. That means that c is a function of the other variable, isn't it? C, in this case, c of z right here. All right, okay, back to the original terms. Exponentiate both sides. This is v of zt, okay, equals to, okay, by absorption, well, e to the negative at. What is this? What is e to a constant? Isn't that just another constant? C of, which is really some function of at, right? That is back to the world of u of x and t. But guys, what is this? What is this z right here? Isn't that x minus ct? All right. That is equal to f of x minus ct e to the negative at, right? And that is the general solution. You don't have to memorize the derivation. I just wanted to show you how do we use the chain rule from Calc 3 with some change of coordinates here to solve pretty basic PDEs here. All right, what matters is to really identify the value of C and the value of A. That's it. All right. Okay, guys, the last example, which is in the next page, actually there are four examples, but I'm going to solve only one, and then I'm going to give you the solution to the other three, because they have similar numbers, just different signs, same condition. But what I want to do here is really show you the behavior of these solutions to the equation. Okay, so number one, here identify C equals to 3 and A equal to 2. So the solution u of xt equals to, what is that? F of x minus, remember? F of x minus ct e to the negative at. Okay? So x minus 3t e to the negative 2t. So that's a general solution. That's it. We're done solving the PDE, this particular PDE, but actually just a general solution. However, what do we want, guys? We want the particular solution. That is, u of x comma 0 equals to f of x minus 3 times 0 e to the negative 2t, which is, in this case, that equals, oh, that's also 0, right? Times 0. So that equals f of x. What is e to the 0? Isn't that just 1? Do we need to write that 1? Not really. But what is u of x 0 equal to? That is 1 over 1 plus x squared. Okay. Do we need to do any shifting? Not really in this case because we just got directly to f of x, which is great. So now change every instance of x with x minus 3t. That is f of x minus 3t equals to, that is 1 over 1 plus x minus 3t squared. All right. And we're essentially done with this. Now go back to the original form right here. U of xt equals to this translation we did over here, which is 1 plus x minus 3t quantity squared, everything in the denominator of 1 times e to the negative 2t. And that is the particular solution given that initial condition. Okay, guys. I would like to have a look at the remaining three examples. You will see how they are essentially the same PDE, the same coefficients, the same condition, the same initial condition. It's just the signs. So I'm just going to use the result of part A to answer B, C, and D, and then I'm going to show you the graphic representation of what this really means. Okay. So notice here this 3 was positive here in the coefficient of the PDE. In the solution becomes negative. The coefficient of the linear term u is positive. In the solution becomes negative. Everything goes the opposite sign, right? Okay, with that in mind, what about the solution for b? So u of xt equals to 1 over 1 plus x also minus 3t, right? Squared. But what about, in this case, e to the positive 2t? Okay, this is positive this time. All right, letter C. Letter C. That's u of x t equals to, what is it? 1 over 1 plus x. Okay, here is negative, goes to positive 3t, e to, squared, e to the negative 2t. Are you guys with me here? What we're doing just changing signs. That's it. That's all it is. And lastly, for letter D, u of x t. Everything is negative. In the solution, everything is positive. 1 plus x plus, yeah, plus 3t squared e to the 2t positive. Okay? Guys, let's have a look at the graphic representations of each of these four solutions and explain why do we call these solutions to this equation what do we call this equation? The transport equation with decay. Okay, so let me hide all of this. Let me hide everything else. So the first one. Okay, check what happens here. For 0. For a equals to 0, which actually I'd like to, let me drag it here. Okay, so that's the solution. And I'm going to give different values of t. Okay, now check, okay, what would you expect for the transport part of the situation? Okay, I'm going to increase the value of a and see how, I guess I need to zoom in a little bit here. I'm going to zoom it in. So number one, okay, let me put this a bit closer. Okay, there you go. So I'm gonna drag to the right, and do you see how the the right the more I go to the right, actually, you know what? Let me change the settings of the slider, and instead I would like to go with increments of, shoot, it doesn't let me type. So when I drag this to the right, it flattened. But what happens if I go to the left? Yes, the shape of the graph gets transported to the left, but also, do you see how the shape of the graph gets actually stretch vertically. Okay, so that's because if we go from right, okay, let me zoom it out. From left to right, we have a decay, right? We have a decay. Can you see why do we have the decay? Because of the negative exponential, right? What about the behavior of the one with positive exponent? I'm going to slide to the right, and you will see how it actually increases instead as we go to the right. Now, another negative exponent here, you would expect to see some decay. However, in this case, for the decay, it actually increases, all right? But that's because I'm going to the left, the transport. So the decay is to the left, okay? And lastly, the last solution, both positive, everything is going to go towards the left, I believe. So if I move to the right, the exponentiation goes to the left, and I mean, it increases to the right. However, the transport goes to also the right, right? Yeah. And that's the visualization of the solutions to these equations. Okay. And